The subject of this webinar is a new publication produced by Joint Fire Sciences Program, funded by Joint Fire Sciences Program, and issued earlier this year. It is a synthesis and knowledge of extreme fire behavior, and this is Volume 1 for fire managers. And later on in the webinar, I will explain why we have Volume 1 and in this section here. But anyway, as I said, this is funded by the Joint Fire Sciences Program, and there was a considerable in-kind contribution by different agencies supporting the co-authors in this project here. So in the fall of September 2008, Joint Fire Sciences Program issued a project announcement requesting proposals for a synthesis on extreme fire behavior. And statement from their website there on what they were looking for is an examination of the state of the science underlying predictions of extreme fire behavior and an assessment of the appropriate uses and limits of this information. So Brian Potter from Pacific Northwest Fire Sciences Lab and myself put together a proposal, and in our proposal we stated that we would synthesize existing extreme fire behavior knowledge in a way that we wanted to connect the weather, fuel, and topographic factors contributing to extreme fire behavior development. We also wanted to clearly delineate the known, the unknown, in areas of future research with the greatest potential impact on firefighter protection. That was our one of our primary goals. And each co-PI, and we had a total of 9 scientists writing different chapters for this publication. Each co-PI was responsible for gathering, reviewing, and synthesizing the existing literature appropriate for their area of expertise. Okay, this frame shows the cover photo, or cover of the publication. And again, this is a combination of Joint Fire Sciences and Pacific Northwest Research Station publication. It was published in the Pacific Northwest as a GTR. And it contains 8 chapters, and 9 authors were involved in writing those chapters. Some chapters were written by 1 author. Other chapters were written by 2 authors. 144 pages, and 7,000 copies were printed, sent to Joint Fire Sciences at the National Interagency Fire Center in Boise, and they distributed them to the field January and February of this year. So it was an early year publication. The publication is also available on the web, 2 sites, www.firescience.gov and www.research.fs.fed.us. And I think Xander is putting those links on the side. As I mentioned, there were 7,000 copies printed, and they're down to a limited number now. So if you don't have a copy, I would say get in touch with Joint Fire Sciences in Boise and request a copy. And if not, you may have to just use the PDF version on the website. Okay, a general chapter outline. All the authors gathered together for a meeting in the summer of 2009, and we determined that the best route for a chapter outline would be each author introduce their subject and then do a summary of current knowledge. And this involved a considerable literature research behavior and fire management tools, and then finish up with knowledge gaps and unknowns, a summary, and then a very detailed literature citation. So that was the general outline for each of the chapters.
Did we lose a slide, Paul?
I'm having a little problem here, Xander, is that my screen is not advancing. Oh, well, we went too far. Maybe my machine is just slow.
Sometimes there's a little hiccup.
Well, there seems to be a big hiccup here.
Okay.
Sorry about the delay there. Anyway, what I'm going to do is go through each of the chapters and give a general overview of the topics that are discussed in each of the chapters. Obviously, we don't have enough time here to go into any lengthy detail, and we may be able to do more detail in the question session here. And looking at the people that have logged in, notice that one of our co-authors on Crown Fire is logged on here, so he may be able to help me answering some of the Crown Fire questions. But anyway, Chapter 1 is an introduction that was written by myself and Brian Potter. And Brian is located at the Pacific Wildland Fire Sciences Laboratory in Seattle, Washington. And you already know my history, good or bad. But anyway, the concept of extreme fire behavior dates back to about the 1950s when George Byram in 1954 coined the term blow-up to describe unusual high-intensity fires. So we're not talking about something that is new to the fire behavior community. This has been around for many years. We did a survey of fire behavior people to come up with what they thought fire behavior conditions were. And we've got many comments back on that, and as you can guess, there's a wide range of comments. One thing we did discuss at our first meeting was the NWCG definition of extreme fire behavior and some of the subjective criteria that they adhere to extreme fire behavior. We discussed among ourselves and came up with a shortened, clear, maybe a little more clear definition that we used throughout the publication here. One thing we did discuss in the introduction here, some of the myths and lore concerning extreme fire behavior, and we also discussed the complexity because extreme fire behavior obviously deals with weather, fuels, and topography, but there is really an infinite amount of combinations of those three variables that can affect extreme fire behavior. The synthesis method was that each co-author was asked to write a chapter on their expertise, field of expertise, whether it be weather, topography, fuels. And we knew that there was going to be a considerable amount of overlapping topics. For instance, in my critical fire weather patterns chapter, it definitely bleeds over into other chapters when we talk about crown fires or wind systems in complex terrain. The literature that was reviewed was primarily peer-reviewed literature, but there was also a considerable amount of gray literature. And that is literature that is presented at conferences, submitted to magazines, that is not peer-reviewed. So there is a fair amount of gray literature involved in here, and probably of any of the authors in my critical fire weather pattern chapter, I used more gray literature than anybody else. Okay, moving on to Chapter 2, that was written by Craig Clements of the Department of Meteorology, San Jose State University. And he primarily discusses wind systems and mountainous terrain in this chapter, at least the first half of the chapter. And those wind systems are either dynamic or thermally driven. The dynamically driven winds are your Fern winds, Chinooks, Santa Anas, Sundowners, Wasso, Zephyrs, Mono, East wind, North wind, primarily wind systems that are pressure driven, pressure gradient driven in the western United States, although the east slopes of the Appalachians also have their Fern-type winds. The graphic satellite picture on the left-hand side of the slide here depicts Santa Ana conditions and wildfires burning in Southern California in 2007. So these systems, Fern winds, are primarily wind-driven winds, but they can definitely be very damaging and really in some areas of the country are the primary pattern for large fires. Okay, thermally driven winds, Craig discusses slope and valley winds and cross valley winds, and fits these into cases where you can have very localized extreme fire behavior produced by these more local winds. He also discusses modeling fire behavior on slopes, a section on explosive fire behavior, chimney effects, and also discussion of inversion destruction and how that can affect fire behavior and extreme fire behavior. Then as far as the wind modeling tools go, there are two primary wind models that are used in the fire behavior business. One is Wind Ninja and the other is Wind Wizard. And Craig discusses both the pros and cons of those two wind models. And then he goes into a summary and future needs, which we will summarize at the end here. Okay, Chapter 3 is Critical Fire Weather Patterns, and that was written by myself. And we want to define critical fire weather patterns as those atmospheric conditions that encourage extreme fire behavior, resulting in large and dangerous fires. There are four primary weather elements that promote extreme fire behavior. And from early on documentation from large fires in the late 1800s, early 1900s, identified strong surface wind and drought as the two primary factors in large destructive fires. And at the time, they didn't have drought indices. They just knew that if there was a long period of no rain, the streams or ponds were drying up, they were in drought. In about the early 1900s, low relative humidity started being studied more. And when I mention low relative humidity, I mean unusually low relative humidity for a particular region. Down the Southwest, it's a lot lower than, say, up in the Pacific Northwest or out in Florida, where it may be relatively high, 35–40%. But there were quite a number of early publications about thresholds of low relative humidity in the Pacific Northwest, the Southeast, and the Northeast. And it wasn't until about the late 1940s where unstable air was starting to be connected with extreme fire behavior or large fires. And part of that is that in the 1930s there were limited numbers of upper air soundings done by balloon or tethered balloons or aircraft, but it wasn't until the late 1940s when the National Weather Service or the Weather Bureau at that time established a network of upper air stations where people could really start to study the temperature profile aloft in some of these large fires. There is a general discussion of critical fire weather patterns, and on the left-hand side of the slide here, I have at the top upper air chart, 500 millibar from the South Canyon investigation report, and pressure levels that we typically look at for critical fire weather patterns are the pressure patterns aloft at 500 millibars, which is the constant pressure map. And then below that we have the surface pressure pattern, which shows the surface pressure or isobars at the surface. So those are the two primary charts that we look at to classify critical fire weather patterns. One of the most prevalent critical fire weather pattern is the breakdown of the upper level ridge. Quite a discussion about that, and some of the best literature concerning breakdown of the upper level ridge comes from Canada. So, fire behavior is international. So we do use publications from other countries in this. After a general discussion of critical fire weather patterns, I discussed the regional critical fire weather patterns, and I broke that down into the Northeast, the Great Lakes, Northern Plains, the Southeastern United States, the Southwestern United States, Rocky Mountain, including the Northern Rockies, Intermountain region, Pacific Northwest, California, and Alaska. And there are unique critical fire weather patterns in each one of those regions. I've also tried to include large fire case studies for a number of these patterns. The next section deals with models and predictive tools, and I broke that up into the Geographic Area Coordination Center Predictive Services products and National Weather Service products. Predictive Services has their significant fire potential outlook 1 and 3 months in advance. That is updated the first working day of the month, so it continues year-round. Each individual coordination center has a 7-day significant fire potential during their fire season, and fuel and fire behavior advisories are issued as necessary, and then there are also briefings, web briefings and such. The National Weather Service products that can be used for determining extreme fire behavior probabilities, red flag warnings, spot weather forecasts, other web services such as briefing. I might add that these products don't specifically address the probability of extreme fire behavior, but rather the probability of large fires or fire problems. And then finish up with a summary section and knowledge gaps. The graphics on the right-hand side picture here are from the Sierra Grande fire in New Mexico, showing the upper level pattern, kind of a breakdown of the upper level ridge, and a fairly strong jet stream moving into the area. In the lower picture is the smoke column viewed from satellite picture. Okay, the next chapter is fire interaction and mass fires, and that was written by Mark Finney and Sara McAllister, both from the Missoula Fire Sciences Laboratory. And fire interactions are routinely experienced on prescribed fires, wildfires, firing patterns used to achieve desired results. And one of the graphics from that chapter is on the right-hand side of the slide here, showing different firing patterns to control the intensity and spread of wildland fire, whether it be prescribed or wildfire. But anyway, the first section of this chapter deals with time-dependent fire behaviors, and we're talking about fire acceleration, length of fire front, flame tilt, spread threshold. And conditions, the next section is conditions where fire interactions occurred. And that is possible, especially when you have many separate fires that grow together, for instance, spot fires. Okay, specific effects of fire interactions. Burning rate can dramatically increase as fires are pulled together. They affect the in-draft, as shown on the graphic on the right-hand side here. Flame dimensions, flame height increases as fires move closer together. They talk about flame temperatures and pollutants. In-draft velocity, again, can increase significantly as one fire is drawn to another. Talked about pulsation. This is important because it can have large influence on entrainment rates and thus heat release rates, and also discussion on convection column that changes when fires interact. As a summary, and basically we can sum this up as fires grow together, they will begin to interact. Burning rate will increase, heat release rates and flame heights will increase until the distance between them reaches a critical level. Needs for further research. They state that there is no clear method to determine the minimum separation distance between two fires for interaction and merging to occur. So this is an area where they see further research would be a definite benefit. Okay, Chapter 5, Column and Plume Dynamics, written by Brian Potter. And plume dynamics refers to the airflow related to a fire's updraft in a way that updraft changes over time. And obviously, plume dynamics can produce extreme fire behavior. Okay, Brian, this goes into the discussion of plume-dominated versus wind-driven fires, and this is really from Byron's 1954 publication. Plume-dominated fires where the power of the fire is greater than the power of the wind. Plume-dominated fires usually show a well-developed and nearly vertical standing convection column. And with plume-dominated fires, fire behavior can change very rapidly, very unpredictable, and very possible that there will be extreme fire behavior noted on that particular fire. Wind-driven fires, on the other hand, the power of the wind is greater than the power of the fire. Basically, the fire is going to be driven downwind, and as such, fire behavior is more predictable. I would say that there is a caveat here that wind-driven fires, if a cold front moves over a wind-driven fire, the flank of the fire can rapidly become the head of the fire. So they, too, can be very dangerous. He then goes into a discussion of adverse wind profiles, that's low-level jets, reverse wind profiles. Again, many of this is from Byram's publication. And then discussion of stability and instability. He talks about the lower atmospheric stability index developed by Don Haynes and is now coined as the Haynes Index, and that is a combination of atmospheric moisture and stability. Downburst and plume collapse. He states that there is no single definition of criteria for plume collapse. Plume collapse is a special case of downdraft, similar to a thunderstorm. A particular study that he references is the Dude Fire by Goins and Andrews, where downbursts were identified as the mechanism for the entrapment of those folks there. And then a summary. Spot fires, also written by Brian Potter. It goes into the spotting process, discussion of the life cycle of embers and firebrands, where they originate. Lofting is determined by air currents associated with the fire. The embers fall back to earth. Do they continue to burn? Do they fall in receptive fuels? Some of this is dependent upon the size of the ember and the effect of the wind, and of course the moisture content of the receptive fuel. This is a graphic that he shows embers being ejected by the smoke column. Okay, management tools. Brian discusses 5 tools that can be used to determine spotting problems. 3 of them by Albini. They basically have an output of maximum spotting distance. One of the other 2 tools deals with the probability of spotting, or that spotting will span a fire break on a grass fire. And the last 2 involve spotting from a single tree. These do not apply to running crown fires. In knowledge gaps, he states the validation of how well the Albini tools currently perform is needed. Existing tools could be modified to include more aerodynamic fuels. Existing tools clearly have stated limitations, so people using those need to understand the limitations of those spotting tools. In the absence of scientific information on a particular fuel's tendency to produce embers, local knowledge is very important in determining spotting process and the spotting problem, obviously. Okay, the next chapter is Vortices and Wildland Fire, and that was written by Jason Forthofer, also from the Missoula Fire Lab, and Scott Goodrick, who is located with the Forest Service at the Southern Research Station in Athens, Georgia. And go into vorticity basics, and basically the definition of vorticity that axis is vertical, we call those fire worlds. If they're horizontal, they're called roll vortexes. And the graphic, upper graphic on the left-hand side here shows ideal fire heat source with smoke column showing vortices on the edges of the smoke column, and then in the wind field, larger vortices around the smoke column. Discussion of fire worlds, vorticity sources. There are many. Wind shear could be a source, complex terrain, frontal boundaries, and then vorticity stretching, or vortex stretching, which is caused by the heat produced by the fire. So you have a vortex that is being stretched as the heat moves that vortex up into the smoke column or around the smoke column. Obviously, increased burning rates and the tremendous spotting problems. Lab results indicate there could be a threefold increase in burning rates when you have fire worlds on a fire. Fire world features. These conditions appear to influence the development of fire worlds on wildland fires. And whirl shedding on the least slope of the terrain or of the plume itself. L-shaped heat source, and there's a graphic on the left that shows an L-shaped heat source in red here, and the vortex developing in the corner of that heat source of the L there. Cold fronts, especially at the time of cold front passage, and that would be directional shear, and then interacting plumes. Horizontal vortices, there's transverse, which is a series of vortices climbing up the upstream side of a convection column. Longitudinal, that's where the axis of rotation is orientated parallel to the mean flow. And they could be single or counter-rotating pairs. And this graphic on the right is an example of longitudinal vortexes in the mean wind flow. The section there on tree crown streets, and some fires have shown alternating strips of burned and unburned fuel. One possible explanation involves horizontal roll vortices, and that's from a publication by Don Haynes looking at the Mac Lake fire in Michigan. The authors also include a summary, which has a table of vortices, type, cause, and potential danger, and that's a nice little summary for the entire chapter right there in that table. Knowledge gaps. Obviously, there's no reliable method to forecast fire worlds or roll vortices on wildland fire. There needs to be a lot more research into the relationship of vertical motions induced by the fire and the ambient cross flow in the development of these vortices. Okay, and then we go on to Chapter 8, and I noticed that Marty is in the audience here, so I hope I don't butcher his chapter too much, and I would certainly encourage him to answer any questions that may arise here on ground fire dynamics. Anyway, this chapter was written by Martin Alexander of the University of Alberta, Canada, and Miguel Cruz from CSIRO, that's the Commonwealth Scientific and Research Organization of Australia. Might add very well-known authors, both of them, in the study of crown fires. So start off with types of crown fires. passive, active, and independent. And the graphic on the left here shows on the x-axis here the rate of spread from low to high, and the y-axis has surface fire intensity from low to high. And for a surface fire, it needs to cross a certain threshold of intensity to become a passive crown fire, and for a passive crown fire to go into an active crown fire, it needs to exceed a certain threshold of rate of spread. Crown fire initiation, intense surface fire is required. Fire line intensity, canopy base height, oil moisture content are important factors in that. Propagation, rate of spread, critical. That also is a function of canopy bulk density. Rate of spread is usually or typically 2 to 3 times when crowning, and there is a sudden increase. The intensity easily quadruples within a few seconds. Flame zone characteristics, the depth, angle, height, length of flame are a reflection of the heat or energy release rate. And there is a graphic to the left there kind of displaying those characteristics of the flaming zone. Area perimeter growth, if the spread rate doubles, the area burned is typically 4 times that of a surface fire. And spotting activity can be intense and is important to the spread rate. Okay, then they go into crown fire models. The Rothermel Guide, which is a statistical model based upon 8 wildfires in the northern Rockies, Yellowstone area in 1988. U.S. fire models, those include Behave Plus, Farsight, Nexus, Flam Map, and others are discussed here. The Canadian Fire Behavior Prediction System is empirically based and is best applied to regions in the United States that have fuel similar to Canada. And I know the Great Lakes and Alaska use the Canadian Fire Behavior Prediction System. There are other empirically based models, crown fire initiation and spread, the CFIS by Alexander et al. Physically based models, discussion of fire tech, Firestar, Wildland Fire Dynamics Simulator, and examples of each. Implication for fire management, practical knowledge and sound professional judgment still needed when using these models. There needs to be a more rigorous program of wildfire monitoring and case study documentation. And for future outlook, research must be directed to both the operational products and the fundamental understanding that forms the basis for such end-user tools. Okay, expected benefits of this publication include these and possibly more. Better understanding of the relationship between weather, fuels, and topography in the development of extreme fire behavior. Future development of better operational tools through additional research. Improved training that includes the fire behavior courses all the way from 190 up through 590. Additional research, and one thing I have been trying to develop here and get someone to host is the Extreme Fire Behavior Library. The literature citations in this publication amount to hundreds and hundreds of excellent studies, excellent publications, and I think we need a central location where these can be accessed. To sum things up, the state of the science at present can best be described as fire is three-dimensional and is not steady state. However, the tools available to us today are two-dimensional and are predominantly steady state. Additional research into extreme fire behavior may one day result in the development of three-dimensional tools. We need to have a greater recognition of the importance of plume dynamics to extreme fire behavior and spotting. Advances in the understanding of fuel structure, especially as it relates to ember production and crown fire, needs to be expanded. Also need a better high-resolution observations on winds in complex terrain to improve the wind models used in fire behavior and spotting tools, and to identify fire whirl potential. One thing, for example, would be upper air soundings on project-sized fires, and I understand that is now possible. Another topic here that should be addressed, the influence of ambient winds or topography on fire interactions. And we also need more research beyond the Haynes Index to quantify the effects of atmospheric stability and fire behavior. Okay, so that pretty much is an overview of Volume 1. And as I alluded to initially, there is going to be a Volume 2, and it is already in the final editing process. The target group for Volume 2 will be fire behavior specialists, researchers, and meteorologists. There's more detailed information in the chapters. I know my critical fire weather pattern chapter includes more case studies. It also includes Canadian and Australian examples. There's an added fuels chapter written by Matt Jolly, Roger Otmore, Russell Partons, and Chad Hoffman. And this is, I think, needed to really complete all the factors involved in extreme fire behavior. So we have added a separate fuels chapter in Volume 2 here. Volume 2 at this time will only be printed digitally as a GTR. And estimated release date, I put down spring of 2013, but it just depends on how fast it gets through the GTR editing process. It may be late spring, early summer. But anyway, look for Volume 2 to come out this next year. And I would entertain comments and questions now.
Well, thanks, Paul. That was a great introduction to all the details available in the GTR, and makes me feel like I need to dive in and read more. So in a second, I'm going to unmute the line, and you can shout out a question. You can also type in a question right now in the chat window. And as moderator, I get to ask the first question. And I'm curious, it seems like there are a lot of research needs around extreme fire behavior, and I guess I sort of have a two-part question. One part is, to what extent can prescribed fires, can we use those in a research context to understand some of this fire behavior? And I guess the other part of the question is, what other options and what kind of progress do you see being made towards some of those research needs?
Well, your first question about prescribed fires, I think there is a great advantage to study more prescribed fires. And I know I think Marty can jump in here too. I know the Canadians have done a lot of intentional prescribed fires, intentionally setting crown fires and studying those. So I think that there is a great deal of opportunities to use prescribed fires or actual projects that that the Canadians, like the Canadians, are doing to simulate and study ground fires. Your second question has to do with research possibilities, and I know that Joint Fire Sciences has been heavily involved in funding some of these research projects, but really, I think that the fire research centers that the Forest Service has is also another good area to gain funding for extreme fire behavior research. As you read through the publication here, you can see that there's been a great deal of research that goes back 50, maybe even as early as 100 years ago, that is still applies to today's physical process of extreme fire behavior. And we need to look at those and expand on those. Couple examples. The reverse wind profile that Byram introduced in the 1950s. The Haynes Index is really the only way we have to account for instability as far as its effect on extreme fire behavior or fire behavior in general. But it is a crude tool, and I believe there's a tremendous opportunity to refine that. Also looking at our fire behavior models, we don't really factor in atmospheric stability. Even the fire danger models are basically two-dimensional, looking at surface conditions and not atmospheric conditions aloft, such as atmospheric stability. So I hope that answers your question, and if anybody has any other comments that they can add here, I'd be more than happy to have someone jump in and put their thoughts in here.
Yeah, that'd be great. And I'm going to go ahead and unmute the line. So all the participants, we should be able to hear you as well. So feel free to shout out a question if you have one for Paul or
Yeah, good afternoon. David Finn from Alberta, Canada. Can you hear me?
Yes, I can.
Yeah, just on the comment about prescribed fire for research, there's two limitations to be aware of. One is that most prescribed fires, if they're done for most prescribed fire uses, are lit under lower percentile conditions, just for safety. And the other one is the engineered ignition aspects of a prescribed fire take away from the research value as opposed to a line fire or line fire with spot fire ignitions that you would have under wildfire conditions. The prescribed fire used for the real research, like the one in Fort Providence, Northwest Territories, those are actually pretty rare because of the extreme hazard conditions that they're burnt under and the preparation and location requirements to run a high-intensity fire without having real conflagration or escape fire. Just a couple thoughts about prescribed fire for research. Thanks.
Thank you.
other comments or questions? Well, I think we're getting close to the top of the hour, and I'm sure that there's a lot to read in the GTR, and people may get in touch with you, Paul, with future questions. And I'm sure there's some folks on the call today looking forward to that volume 2. So unless there are other questions, we can. I'll shut down the webinar, and you'll get the participants will be sent off to a survey, and I encourage everybody to fill out the survey when they have a chance. And I will follow up with an email that has a link to the recording of this webinar in case you want to share it with your colleagues or other folks who would be interested. So any last questions? Well, Paul, I want to thank you again. I really appreciate you taking the time to introduce us to the GTR, and you did a lot of great work on this, so thank you.
For allowing me to present this.
Okay, and with that, I'll go ahead and shut off the phone line and dismiss folks from the webinar.
Thank you.